So, as it says here, chemical and physical changes. We learned a little bit about the difference, but we really want to dig down into what this means today because, fine, come on. All right, stay there then. So let's look at some examples. So a classic example, and one that I saw a lot of high school students had a problem with when I was volunteering in the San Francisco schools, was realizing what happens when water changes its phase. So I think most people are familiar if, oops, let me draw on this, that the changing water we normally see as a liquid. So we put the state of the compound in brackets. And then when we remove heat from it, it becomes a solid as ice. And so we put S there for solid. Now, is that a chemical reaction or a physical reaction?
Physical reaction.
Okay, why?
The chemical compound isn't necessarily changing. We're just changing the state of the matter.
Exactly, excellent. Yeah, it's still water. Notice that I have H2O on one side and I got H2O on the other side. So nothing has happened chemically to the compound. It has changed state. It has gone from being in a liquid state to being in a solid state, but it's still water. But what happens if I add heat? And when we add heat, we put like a little a triangle there, usually to indicate the addition of heat. What are our products when we add heat to liquid water? So if we remove heat, we get a solid. But what if we add heat back? What do we get?
It would become a gas.
Does it stay H2O? I agree. A gas is the product, or at least one gas is the product, but does it stay H2O?
Would it just be hydrogen and oxygen itself in the air?
See, this is where the confusion comes in, because when I was, teaching the high school chemistry class, I'd ask the students the same thing, and that's what most of them would say. You would get hydrogen and oxygen. Oops, and I can't spell. So hydrogen and oxygen. That would be H2 and O2. But is that really what happens?
No, I don't think anything's dissociating the hydrogen and oxygen in water.
So are we getting H2 and O2, or what is the product when we add heat to liquid water?
H2O.
It's what?
Steam,
Steam, exactly. What's steam?
a byproduct of hot water.
What is it though, chemically? What is it?
Would it still be H2O?
It is, exactly. Steam is just H2O gas. So the product of adding heat to H2O liquid is just H2O gas. So basically it's changed phase again. And the only difference, as we sort of learned early on, the only difference between a solid, a liquid, and a gas is basically the distance between the molecules. In a solid, they're right next to each other, pressed up against each other. In a liquid, they're able to move around, but still fairly compact. But in a gas, there's a huge distance between the molecules because they have a lot of energy and they're moving around very quickly and there's a great deal of distance between them. But chemically, they're identical. There's no difference. And so these are all physical changes. What has to take place for a chemical change? Something has to happen for it to be called a chemical change. What has to happen? We sort of learned a little bit about that this morning. What did we talk about this morning?
Chemical bonds.
We talked about chemical bonds, exactly. So for a chemical reaction to take place, what needs to happen to those bonds?
Would they either be forming or, I guess, bonds would break as well?
Exactly. Oh man, you're crushing it today. That's exactly what it means. So let's look at, let's take water again as a liquid. But instead of putting heat in, this time I'm going to put in electricity. So when I put electricity into water, I do get separation. What happens is these chemical bonds between oxygen and hydrogen, so these are the chemical bonds between oxygen and hydrogen, they break. And then new bonds form between the hydrogens and the oxygens. And so I get H2 and O2, both gases. So that is a chemical reaction because we're breaking these oxygen-hydrogen bonds and we're forming hydrogen-hydrogen and oxygen-oxygen bonds. So that is a chemical reaction. So anytime a chemical reaction takes place, even if we go from a liquid to a gas or a gas to a solid or whatever, that's not the important part. The important part is bonds are broken with our reactant. So bonds are always going to be broken in the reactant, and then new bonds are going to be formed in the products. So that has to take place for a chemical reaction to take place. And so what we're going to learn with these particular experiments is how to spot that, because it's awfully difficult. I mean, atoms are obviously super, super, super small. How are we going to know whether or not bonds have broken and bonds have formed? And there's a couple of ways to tell. So physical changes, as it says here, physical changes may look for a change in the appearance of something, but it doesn't mean that the chemical composition has changed. Just like we showed with water being either can be steam, or it can be liquid water, or it can be ice. All three are water. But chemical changes, we break bonds in the products and then we reform new bonds, or we break bonds in the reactants and reform new products, new bonds in the products. And some of these things are things to look for, are sort of telltale signs, like the production of a gas, for instance. And that would have been shown when we do what's called electrolysis of water, adding electricity to water. If we put electrons in, that breaks the bonds in water, and then we reform new bonds in the hydrogen and oxygen. And then we see gas forming, hydrogen on one end of the battery, oxygen on the other end of the battery. The other thing to look for for a chemical reaction is if you take two clear solutions and you mix them together and you get something insoluble crashes out, an insoluble solid. We call that a precipitate. That often happens when we have ionic compounds. If I have a solution with one ionic compound in solution A, and that cation and that anion are soluble when they're together, And then I have a solution of B that has a different mixture of cations and anions that are soluble together. When I mix them, then a new cation mixes with a new anion, and they're no longer soluble, and they crash out of solution. And generally, you will see it's not always super dramatic. We see these huge crystals forming. Sometimes you'll see like a suspension, like a milky suspension. If the crystals are really small, you see basically you'll see a suspension. A lot of times you'll see a color change as well. Like for instance, lead. The reason why lead was used in paint for so many years is because by changing the anion associated with the lead cation, you get these beautiful colors. Like lead iodide forms this beautiful yellow color. It's really pretty. Of course, it's also super toxic. So that's the reason we sort of got rid of lead in paint. But the reason why it was there for so many years is because it formed these beautiful reds and yellows and blues and greens, depending on what anion it was associated with. Another thing to look for that indicates a chemical reaction is the production of light. So light comes from when electrons are excited. Remember, we talked a little bit this morning about where electrons are in an atom, how close they are to the nucleus. Well, when an atom gets excited, those electrons will shoot into like really high energy levels. And then when they come back down to the lower energy level, that energy from going from a high energy to a low energy gets released as light. And so a lot of chemical reactions, you will see that. You will see electrons being excited and then returning to their normal place. And so you'll see blue light, yellow light, red light, all sorts of different colors. But a lot of the time, it's a sort of giveaway that some sort of chemical reaction is taking place. Also, the production or absorption of heat. So when you light a match, and that's actually, one of the simple experiments you'll do today is actually just lighting a candle. And there's a lot of things going on that are indicative of a chemical reaction. And your job is to note each and every one. So, there's products being produced. There is heat being produced. There is light being produced. There's all sorts of different things happening, all indicating that there's some sort of chemical reaction taking place there. Bless you. And as I mentioned, color changes. Now, not all color changes are the same, and that is one of the experiments you're going to do today. Like for instance, if you took blue food dye and yellow food dye and mixed them together, what would you get?
Green.
You get green, right? Is that a chemical reaction?
No.
Not really, because that would be expected, right? And another way to think about it is if I had a glass with like some blue food coloring in it and another glass with green food coloring in it, and I put them if I look through both of them at the same time, I would see green, even though the yellow and the blue didn't even come in contact with each other. So obviously that can't be a chemical reaction. But if I look through the two of them, it's green. If I move one away, it's yellow or blue. And if I move it back, it's green again. So that isn't a chemical reaction. That is a simple physical change of there being both yellow light and blue light sort of mixing together and forming green. That's just going to happen without a chemical reaction. Generally, when we say we're looking for a color change, is if one that's completely unexpected, like for instance with the lead iodide here. If I had lead ions in solution and then I added sodium iodide, which is a salt. If I just added sodium iodide to that, I would get these beautiful yellow color being formed, this yellow suspension. That is a chemical reaction because I had something that was clear. The lead solution was clear. Sodium iodide was colorless. It didn't have any color either. So when I mixed two colorless things together that made a new color, that is a chemical reaction because that's unexpected. There's no way to see that as just two colors mixing together to create a third. So that's something different to look for. Let's have a look at some of these reactions. So you're going to need a lot of material. There's a lot of stuff here to do. So that's why we're going to take a little bit of time and dig all these out. So sodium carbonate. Carbonate is CO3 with a -2 charge. So we're going to need some of that, and that comes in an eyedropper bottle. This is a fun reaction. Sodium polyacrylate is basically these really small crystals, and we're going to add water to it and see what happens. So the aluminum weigh dishes, there's some in the, if you can't find those immediately, I know there's some in the reaction for the hydrate reaction. It's in a bag called measuring hydrate of salt. I think we're probably going to do that experiment maybe in a week or two. Iron nail, there's a whole bunch of test tubes in there. This is the test tube rack, and all you need to do is just fold it, and it makes a nice little rack to put test tubes in. Obviously, you don't want to get this thing wet because it's just made of cardboard, but it's great for keeping things from rolling off your table. We'll need more of the plastic cups that we used last week. These medicine cups are smaller. They're about, I don't know, maybe half to a third of the size of the plastic cups. We're gonna need our balance again. Thermometer is going to be critical for this experiment. So find your thermometer. Unfortunately, we don't have the digital kind, though if you do have the digital kind, that works great too. But we're going to be measuring the temperature of pretty much all these reactions because we want to see whether the temperature goes up or goes down. If the temperature goes up during our reaction, what kind of a reaction do we call it? Anyone remember from high school? Basically, it means that heat is being given off by the reaction. Heat is leaving the reaction. And so the temperature goes up. What do we call that?
Exothermic.
Exothermic, excellent. Exo meaning outer. So the heat is going from in to out. It's being released to the surroundings. What if the temperature goes down during our reaction? What do we call that?
Is it endothermic?
That's endo, right? Endo meaning inner. So the heat is going from the outside in. So the reaction is basically taking heat from the surroundings and turning it into the chemical reaction. So weigh boats, beaker, we need to find all this stuff. Then what you'll need is just a little bit of sugar, not nearly as much as last week. A little bit of table salt, ice cube, have some filtered water around, and some matches because we're going to play with fire this week. So also yellow and blue food coloring are in chemical kit 1, although my son bakes so much we've got like food coloring all over the house. And then these are hydrochloric acid. You're definitely going to want to be careful with that. We will be wearing our goggles today because hydrochloric acid and sodium hydroxide are both very strong solutions. This is a strong acid, and this is a strong base. And most people are familiar with strong acids being dangerous, but actually strong bases are even more dangerous than strong acids. You could burn yourself with a very strong acid. These are like about 1 molar, so it's not terribly dangerous. If you do spill a little bit of hydrochloric acid on yourself, just rinse. You can just rinse it off with water before anything bad happens. But with the strong base, anyone knows what happens when you mix a strong base with fat? What that makes? And it's actually an experiment we can do later on in the term. Makes soap. And so a lot of times if you spill a strong base on your skin, or even if you get the solid on your skin, you don't feel a burn at first. You just feel like it's getting slippery. And that means basically it's turning your skin into soap. And so you definitely want that to stop as quickly as possible. So anytime you spill anything on your skin, you're just going to want to just run it under the water for like, 5 minutes or so, just to make sure you clear everything off that. And copper sulfate isn't terribly dangerous, but it will stain your skin. Copper 2 has a very strong blue color. So when we have copper 2 ions, they're blue. And we have copper 1 ions, they're generally green. So does anyone know what the Statue of Liberty is made out of?
Copper.
Copper. And you know what the color of the Statue of Liberty is?
Green.
It's green. Yeah, because that is copper being oxidized by oxygen. And so it's green. So you're not going to want to get it on your skin because that blue color will stay around for a while, but it's not particularly dangerous. And we want a little bit of magnesium ribbon. So that's just basically long, thin, relatively shiny, though not really shiny. It does sort of have some dark color on it. The dark color on it is, anyone know what there's like a thin layer of something on the magnesium ribbon. You want to take a guess what that might be? Thinking about the Statue of Liberty.
Is it oxidation?
It is. It's oxidation. It's magnesium oxide. So magnesium is desperate to give away those electrons, and oxygen is none too happy, more than happy to take them from them. So most metals, a lot of the metals that we deal with are going to have oxide layers. And so magnesium, usually before we use it, we get a little bit of sandpaper or something we can scratch it up with. Because you'll notice that if you take a little sandpaper to the magnesium, then it gets like really, really shiny. That's why gold and silver and platinum and all so-called precious metals are precious, because they don't oxidize nearly as quickly as most of the other metals do. And so most other metals just get these oxidation layers on them really, really quickly. So they go from like nice, pretty shiny objects to getting all tarnished and dark and everything else. But gold and silver and platinum, palladium, other metals like that, takes a really, really long time for them to oxidize. So it's like gold will stay shiny for thousands of years before it oxidizes. And that's why they're called precious metals. So we're going to read through, hopefully you've read through the procedures already. You want to get all the materials together in one place, and then start getting your solutions together. So the first thing you're going to make is 10 mils of water in the 2 small cups. That's what we'll use the medicine cups for. And just add a drop of yellow number 5 to 1 cup and blue number 1 to the other. So, and then water. Hopefully you want water at room temperature for pretty much all these experiments. We don't want to, because that way it makes it sort of easier to measure the temperature either going up or going down. If you use hot water and it's an exothermic reaction, you may not be able to tell because the water's hot already. Or if it's an endothermic reaction and you're using very cold water, you may not be able to tell because the water's already cold. And this here is sort of just an indication of, this is why we have this little band on the thermometer. It really helps because it doesn't roll off the end of the table. So it's incredibly helpful. If yours doesn't have one, you can just get a rubber band and wrap it around a couple times. But it's really helpful because you can easily lose that or break it or something like that. Right, let's have a look at some of these reactions we're going to do. All right, so the first one is looking at hydrochloric acid, which is HCl, and sodium carbonate. So we have two test tubes. So about 2 mils of the 1 molar hydrochloric acid. And remember, if it says 2 mils, it doesn't need to be exactly 2.0. If it says 2.0 mils, then you got to get it like super accurate. But if it says 2, basically anything between about 1.8 and 2.2 mils is fine. It's just roughly that much. Rinse the graduated cylinder once you've added the HCl. And then 2 mils, again, around 2 mils of the sodium carbonate solution. And then record the temperature of the hydrochloric acid. It should be room temperature, whatever your room temperature is. And then combine them. So measure the temperature of the acid, measure the temperature of the sodium carbonate. They each should be room temperature. Mix them together and then measure the temperature of the product. So you want to, for all of these reactions, you're going to want to look for changes in color, production of light, production of heat or lack of heat or the temperature going down, or the production of a precipitate every time. So this is the first one we'll do. So the next one's kind of fun. I'm going to do this one with you. So sodium polyacrylate, like I said, it's just basically it's a polymer, and it comes in basically like a small, like really small round crystals. So you put 10 mils of water in a test tube, 0.3 grams. We're going to we measure 0.3 grams of the polyacrylate. I think you have 2 grams. There's plenty left over. Look at the temperature, measure the temperature of the water, and then dump the water and the sodium polyacrylate, put the thermometer in, measure the temperature, look for changes in color, look for light. And then how you're going to write your report is basically recording all of these different things you're going to see. So, and then explain whether a chemical or physical change. So you're probably going to have to throw this in the trash, the test tube as well. Don't worry about it. We have lots of test tubes, and it's safe. Don't worry. All of the reagents we use are safe to toss in the trash. So it's nothing poisonous or anything like that. And then copper sulfate and sodium carbonate. So this is one of those reactions that I mentioned before that you're going to have. This is an ionic solution. And this is an ionic solution. We have copper 2 ions with sulfate ions in one solution. And we have sodium ions and carbonate ions in another solution. Then when we mix them together, we'll have all 4 of those ions in one solution. Now, while copper may be soluble in the presence of sulfate ion, and sodium may be soluble in the presence of carbonate ion. We don't know whether or not copper 2 ions are soluble in the presence of carbonate ion, or whether sodium is soluble in the presence of sulfate ion, although sodium is basically always soluble. It's super, super soluble. So again, about 2 mils of each one in different test tubes, measure the temperature, mix them together, and then put the thermometer in and see what happens. Does the temperature go up? Does the temperature go down? Are colors produced? Is a precipitate produced? Is light produced? And so on. And then basically we're just going to dump all of our waste into the 250 mil beaker, and then rinse the test tubes with water, and then dump those into the beaker as well. And at the end of it, you can just take the beaker and pour that stuff down the sink, because all this is stuff that can easily go in the wastewater. It's not a problem. So number 4, we're looking at a burning candle, looking at an ice cube. Fairly straightforward. So you light the tea candle, and we basically are looking for, can you see anything occurring? Again, you're looking for the same 3 things. You're looking for the production of light, production of heat, production of a precipitate, production of gases. Are any of those taking place? And then the ice cube, I think you can pretty much tell what's going to happen with the ice cube. It's going to melt, right? So basically observe the thing melting, and do you see anything else? And then record your observations. Number 5, at making a sugar solution. You're going to see the temperature change when you add water to sugar. Now, does anybody, when you add sugar to water, now do we suspect that this is going to be a chemical reaction or a physical reaction?
Is it a chemical reaction?
What? Well, why would you think that? Let's sort of go through it.
Because when you dissolve sugar in water, doesn't it disassociate the ions in sugar?
Is sugar an ion?
Oh, well, doesn't it break the bonds between the sugar?
It doesn't actually. Sugar, we're going to learn, is not an ionic compound. Sugar is a covalent compound. So when you dissolve sugar into water, you do not break the covalent bonds in sugar. In fact, most, if not all, covalent compounds, when you dissolve them in water, the ones that are water soluble, all they do is just become dissolved in water. And so what we would call that is sugar AQ. Anyone know what the AQ stands for?
Aqueous.
Aqueous, right. It just means it's dissolved in water. So this is sort of giving it away. This is a physical reaction, because now the only thing that happens when you take sugar and put it in water, that sugar basically is interacting with itself in crystals when it's just a solid. And then when you throw it into water, water then surrounds each sugar molecule and breaks those crystals apart. And now each individual molecule of sugar is surrounded by water molecules, but they don't break any of the bonds. And so you need to see if you can tell that based on your observations. Shouldn't have given that one away. So anybody know what this stuff is? Maybe you've heard of it. Phenolphthalein. It's a fun word to say and an impossible word to spell. You know what it's used for?
It's an indicator.
It is an indicator. An indicator of what?
Is it a pH indicator?
It is, exactly. It's a pH indicator. Excellent. So it changes color depending on whether the solution is acidic or basic. Acidic means the pH is below 7. And basic means the pH is above 7. And phenolphthalein changes color around pH 8, around pH 8 or so. So is the pH of a sodium hydroxide solution going to be basic or acidic? Is sodium hydroxide a base or an acid?
It's a base.
It's a base, right? We'll learn more about that in a couple chapters. It's a base. And so when you add the phenolphthalein, see what the color is, and also measure the temperature of the sodium hydroxide. Then do the same thing. Oh, and save that test tube with the phenolphthalein and sodium hydroxide in it. Then get another test tube, and again around 0.2, around 2 mils of the 1 molar hydrochloric acid solution. So is that kind of a giveaway? Is that an acidic solution or a basic solution? HCl.
Acidic.
That's acidic. Yeah, that's acidic as hell. Yeah, so that's going to have a very low pH. So when you add the phenolphthalein to that, or what you're going to do is add to the NaOH, or the sodium hydroxide phenolphthalein solution. See if that makes a color change, and also put the thermometer in it and see if it makes, see if it releases energy. It's an exothermic reaction, or whether it takes in energy, lowers the temperature for an endothermic reaction. So note the change in temperature, the change in color. Is there a change in, is there a precipitate? Is there light? Basically, we're looking, every one of these reactions, we're looking for all 4 of those things. So now we're going to use the sodium hydroxide again. This time we're going to mix it with copper 2 sulfate. And sulfate is SO4 with a -2 charge. So it's always that charge. So if there's a single copper associated, then we know automatically it's copper 2. So copper 2 has that really pretty blue color that I mentioned before. So you'll have one test tube with copper 2 sulfate in it, and another one with 2 mils of sodium hydroxide. Measure the temperatures again, add them together, and then look for color change, light produced, precipitation. So again, that should take, about 2 minutes to do. And then this is just taking that blue and yellow food color solution you already made. Again, just measure the temperatures of each one, mix them together, see if you can detect any sort of chemical change. This is a fun one. So we're going to be doing this reaction a little bit later and looking at the products of it. We're not going to look at the products this time, but this time you want about 5 mils of hydrochloric acid in a test tube. Get the magnesium ribbon and measure about half a centimeter or so. It's going to be really easy to cut. You can just use scissors, but I would recommend, if it's really, really dark in color, to just get, if you have something to scratch it up with, if you had some relatively fine or even relatively coarse sandpaper, works great. Or if you have a file, that works as well, because that will help the reaction go. Because if you don't do that, then basically you've got magnesium hydroxide trying to react with hydrochloric acid, and we want the magnesium metal reacting with the hydrochloric acid. So again, just drop the magnesium ribbon in, sort of give it a general swirl, add the thermometer record the temperature and any other observations you might have. So with these, as I mentioned, you're going to want to wear your goggles, because if you splash hydrochloric acid or base or sodium hydroxide in your eye, it's super, super bad news. So you're going to want to have your goggles on for each one of these experiments. Then we're going to take the copper sulfate and add just straight up sodium chloride to it. So now we have copper 2 ions, and we're going to have sulfate ions in solution. And then to that, we're going to add sodium ions and chloride ions. So we want to see what happens when we do that. See if there's a change in temperature, see if there's a change in solution, see if a precipitation takes place. Save that solution, because there's one more experiment we're going to do with it. And that's the next one. So take that same solution and we just get some aluminum foil. And I think pretty much everybody's got aluminum foil at home. If you don't have aluminum foil at home, you just take pieces of the aluminum disc, just cut little pieces of it, and throw those into this solution of copper 2 sulfate and sodium chloride from the last one. Measure the temperature, should be the same temperature as it was that you measured last. But see what happens when you throw the aluminum in. It's pretty interesting what happens. What's the color of the aluminum? Well, silver and shiny. What happens to that color and any other else? I think you're going to like this one, because there's a lot of weird stuff happens in this reaction. And then finally, we've got copper 2 sulfate and an iron, a piece of iron. I think it's just a nail. So that's just straight up iron, no charge. So we're just going to take the copper 2 sulfate, put about 5 mils in, and then put the nail in it. So again, if the nail is really dark in color, it has iron oxide on the outside. So again, you might want to either, polish it up a little bit so it's a little more shiny, and then dump that in there, look at the change in color, and then take your forceps to remove the nail out. Again, look at measuring the temperature of each one. So your report is going to be really, really simple. Basically, it's just what were the color of the items when you put them into the test tube. When you mix them together, what color were they after that? What was the initial temperature, the final temperature? What did you see? Now, put things more like, when you're looking at the candle or something, just putting it burned isn't a particularly good observation. You want to give colors that you see. You want to give, potential, gases that you might see. Is it smoking? Is there black soot coming off it? All that kind of stuff you want to include in your observations. Then you say whether it's chemical or physical, and then explain why. With the criteria we talked about at the beginning: change in temperature, change in color, production of a precipitate, production of a gas, all those things. Which one of those did you see? Did you see more than one? And then put those in as your explanations. All right, so any questions before we get started? Like I said, there's a lot of these little experiments to do. So there's a lot of stuff to get together. Any questions before we begin? Nope, everyone's good to go. All right, so give everyone like 10 minutes. We'll start at 3. So we got like 12 minutes. So I'll pause, get all your stuff together. Oh, Karen, yeah, we don't need to fill the temperatures out for 4A and 4B because one is on fire and the other one is frozen. So yeah, that's why. Yeah, when I first saw that, I wonder what that was about too. But the nibble, we don't want to put this into the flame, and the color of ice is 0. Not the color, the temperature of ice is 0. Yeah, so we'll get it. So at 3 o'clock, we'll all come back together, and we'll all have our goggles on, and we'll have our cameras on, and we'll get started. Okay. All right. I'll see you in a few minutes. Start the recording back up again. So like I said, you can do them whatever order you like. I'll be here to answer questions while you're doing it. But you can see the sodium polyacrylate, it's like really, really, really fine powder. So remember to use your weigh boat, because we never want to pour things directly on this. Unfortunately, if we were in the lab, you'd see that the balances in the lab are pretty rough shape for people spilling things on them. So test tube, here's my test tube. And just tap it, get my 0.3 grams in there. And I use my handy dandy holder. So I want 10 mils of water. Where did I put my 10 mil? Just had it. Where did I put it? Oh, there it is. So this is going to be more accurate because it's, goes to 10. Where's my 10? It's going to be more accurate than the 50 mil. And so basically we're going to be using this for all the measurements today. So 10. There we are. And I want to measure the temperature before. So I'm going to just do a quick measure the temperature. Yeah, you never want to hold the thermometer by the bulb, obviously. Yeah, the water's fairly cold. It's strange. Leave that there for a minute. So, I got like 10 degrees. So my filtered water must have been in a cold part of the kitchen. So when you mix, generally you don't want to shake these. You sort of just gently tap it with your finger like this.
Professor, which activity are we doing? Or
You
you
do whichever one you like. I'm doing number 2.
Okay.
Yeah, because there's so many of them, you can do them whatever order. So you can see that it's gotten cloudy. The water has definitely gotten cloudy. And is now a solid. So I'm also going to put my thermometer in there and see if it's changed color at all. See if it's changed temperature. And I'll put it down because I don't want the heat from my hand. Temperature has not changed. It was 10 when I put it in, and it's 10 degrees now. So no change in temperature. But you can see that those very, very fine crystals that are really, really small have gotten big. They have increased in size tremendously. And basically increased so much in size that they now fill the tube entirely. So the question for you would be, is that a chemical reaction or is that a physical reaction based on your observations? Was there a change in color? Was there a change? What did it precipitate form? Something insoluble that wasn't insoluble before? Was light released? Was heat released or absorbed? Take all those down and then decide whether that was physical or whether that was chemical. I'm going to go clean this off because we need it for the other reactions. Yeah, so all this stuff is safe to, you may not want to put this solid stuff down the sink or just like wipe it off and then put it in the, this might clog your sink up. So which one are people working on, and what are you seeing?
I'm doing activity 1 with
Mhm.
the hydrochloric acid and sodium carbonate.
Okay. So has anyone added them together yet?
I just did. I still have a colorless solution.
Okay. Did the temperature go up or down?
There was a slight temperature change going up, about like 1 degree going up.
Okay. That counts. Not all these things are going to be, there's a couple in there where the temperature change will be fairly dramatic. But yeah, I don't think there's, most of them, you're not going to see a really large increase in temperature one way or the other. See, which one should I do next? I'm gonna do the copper. Okay. All right, got my copper sulfate. Got my sodium carbonate. Notice that on these bottles, like on the copper sulfate bottle, it has copper 2 sulfate. So we learned what that was. Anyone know what this 0.5 M means? What does that mean?
It's a concentration of the
That's
Molar.
right. It is a concentration. Excellent. What does the unit capital M stand for? Do you know?
molarity,
Molarity, which is
grams per liter. Oh wait, moles per liter.
moles per liter. Excellent. Yeah. When we do reactions involving liquids, it's really easy to figure out how many moles of something we have, because the concentrations are given in moles per liter. So we don't have to weigh anything, which is great. All we have to do is measure the volume. So 0.5 molar, that's what we call capital M, means that there's a half a mole of copper sulfate in every 1 liter of this solution. So all we need to do to figure out the number of moles is figure out how many liters we're adding to something and multiply it by 0.5. And then bingo, we have the number of moles. Same is true with our sodium carbonate. Sodium carbonate has 1 M on it, meaning that instead of 1/2 of a mole per liter, it has 1 mole per liter. And the same goes for, I think, for the sodium hydroxide solution, I think is 1 molar. And I think the hydrochloric acid, the HCl, is also 1 molar. There's my 2 mils of sodium carbonate. I rinse this out with some water. And also measure out 2 mils of the copper. Or the other thing you could do is if you have the same size, test tube, you can just put them right next to each other and bring them to the same level. Since we don't have to have exactly approximately 2 mils, we can save ourselves a step and do it that way. So I think I might just do that. Okay, we have about the same amount in each one. So we would notice that our copper 2 solution is this really pretty sort of aqua, more blue, I guess, than aqua. Of course, I'm looking at it against the screen. And my other solution is colorless. I put them together and I mix. And you can see, so what happened here? I had 2 clear solutions. I add them together and I get this. What do we call that? Is this a soluble solid?
Is it a precipitate?
That is a precipitate, exactly. That is a precipitate. Did the color change?
It went from clear to like opaque, right?
Is that the change in color though?
No.
Because this was the color, this is the color of the copper 2 sulfate solution. And this is the color of the precipitate. Would you say that those two colors are the same, or are they different? Kind of hard to see.
Different.
Okay. Everyone sees color a little bit differently. So I don't know. Maybe
Well,
you're right. I mean,
'cause
this
the
looks a
state
little.
of it changed.
Oh, go ahead. What was that?
The state of it changed because it was like full liquid. Now it's
Mhm.
like solid, so it
The state
changed
definitely
the color
changed.
a little bit.
It may have. I'm not sure it does though. I mean, because the original solution is kind of blue with a little tinge of green in it. And then to me, that looks blue with a little
I thought it was just
tinge of green in it.
stained from the bottle.
No, I mean, this bottle is not, I mean, it's not completely clear, but it's not adding anything to the color. It's the solution in it that's blue. Let's sort of do a quick review on that, on what that could be. So let me just share this. So we had two different ionic solutions, and we'll learn that when we have an ionic solution, what that means is that those ionic compounds actually break down. And so if I take solid copper 2 sulfate, solid, and I add that to water, what happens is that those two ions separate and are released from each other. So now I have copper 2 aqueous plus sulfate ion aqueous. So this is what's actually in solution. I don't have copper sulfate in solution, really. What I do is I have copper ions in solution and I have sulfate ions in solution. They're no longer interacting with each other. They're now completely surrounded by water. So water is surrounding them and keeping them from coming together. So I have this solution. I also have this solution, sodium carbonate. So I put that in water, and now I have sodium ions and carbonate ions in solution. So when I mix them together, this is now what I have all at the same time in my test tube. So the question is, what new compounds can form out of this? So there's only two potentially new compounds that can form. We can either make sodium sulfate, or we can make copper carbonate. Now, as I mentioned before, sodium is pretty much always soluble. Sodium is like really, really, really small. Sodium ion is like super, super, super small and super, super, super stable. So it basically will stay in solution all the time. because it's just as happy as a clam being sodium ion. On the other hand, I've got copper 2+, and I've got carbonate ion. And when they get together, they make this. Now, the question is, which is more likely to be insoluble? Copper carbonate or sodium sulfate? Because we know that copper sulfate is soluble, because we have copper 2 and sulfate are both mixed together in solution and they don't precipitate. So we know that this plus this is soluble. We know that this plus this is soluble. So the only two things that could form this insoluble compound is either this or this. One of those two has to be insoluble. And as I mentioned, because sodium is just generally super duper soluble, this is going to still be soluble. And the other thing that sort of gives it away as it being the copper carbonate being the insoluble partner is that look at the color of the crystals that formed. They're bright blue. Well, what forms bright easy for me to say. What forms bright blue crystals? Copper 2 does. And so this is our insoluble compound. And so the overall reaction is copper 2+ plus carbonate aqueous makes copper 2 carbonate solid. And the other way that chemists show that the insoluble precipitate is made is they put an arrow pointing down. So that means it's falling out of solution. It's a solid, it precipitates, it falls to the bottom. A lot of times if a gas is formed, like if H2 gas is formed, sometimes we'll put an arrow going up, basically saying that it's being released. It's a gas, it's coming out of solution and going up. So that is the story behind this particular solid. And I think there's I have to double check. I think there's a solubility table on our reference sheet for tests. I think it gives a whole list of ions that when you mix them together will precipitate. I think that's there. And if it isn't, I'll put it there. It's not a main thing we're going to be studying, but it is something I want you to be aware of what a precipitate is. It's when you take two soluble ions, you mix them together, and it forms an insoluble ionic compound. And that's what we saw with the copper.
Professor, for the all the observations to say whether there's like a production of gas, production of precipitate, light or heat, color change. But if there's nothing, should we just say that there's like mixed and like colors stayed the same? Or you just want it?
That would be your observation. Yeah, I mean, if you mix two things together and they didn't react, then you'd have to give some evidence as to how do you know, right? So what did you see? And if it was you didn't see any color change, you didn't see any gas produced, you didn't see any precipitate, you didn't see any color change, All right, looks like it didn't react then.
Thank you.
Yeah. Ooh, number 6. I think I'm going to do number 6. So how are people doing so far? Have you've what did you see with number 1?
I saw nothing change. I mean, the temperature kind of increased. But there was no like color change.
Okay. And that's
Or
someone else saw that too. Is that Mac? The color went up, the temperature went up a little, or is that Ryan?
The temp went up by like 1 degree. I mean,
yeah,
By how much?
by like 1 degree because I started
Yeah.
out with like 24.2
Oh
and it
man,
ended up
nice,
being like 20.
nice and
yeah,
toasty
20.
where you are. Where are you living? Yeah, it's not that warm down here because I live in Pacifica. I don't think it ever gets to 24 degrees.
so because there was like that slight change in temperature, that's still like producing heat.
That still
So-
counts. Yeah.
okay.
Yeah. I mean, these things are going to burst into flame, right? I mean,
Mhm.
some of these changes are going to be fairly subtle, which is why we sort of need to sharpen our, observational skills.
Mhm.
So yeah, 1 degree difference is definite. That's a thing, Of course, we can't keep measuring it indefinitely because eventually that heat from that reaction will just be given off out into the, universe, and the temperature will return to room temperature. So basically, when we're recording the temperature, we want the highest temperature achieved. So normally we measure it for like, I don't know, maybe 5 minutes. And then if it goes up, we keep an eye, we write down what it was. And then if it starts going down again, then that's it. We don't have to keep measuring it. We just want to measure it at the highest point.
I have a quick question.
Mhm.
For the activities, when we switch using like between each activity, do we have to rinse the thermometer and like the
I would, yeah.
do we rinse it with the like regular tap water work, or does it have to
Oh,
be?
sure. Yeah. I mean, distilled water or filtered water is better because, as you've seen, a lot of these reactions involving precipitations involve ions, right? So tap water has iron ions, and it's got calcium ions, got a lot of calcium ions, and it's got, copper ions. And if you're unlucky, it's got lead ions. So you don't really want those because they may interfere with these sort of things, but you do what you can, right? So it probably won't make a big difference because the concentrations of those things will be vanishingly small. But if you were doing like an actual, like, real experiment, yeah, we would definitely not use tap water for anything. You could use it for like washing stuff out, but then you would rinse it with distilled deionized water before you used it for anything. Right, let me get my stuff together for number 6. Okay. Yeah, I love that color. It's really pretty. It reminds me of what's that stuff they're always making belt buckles out of, like in the Wild West. Oh, turquoise. It's sort of like a turquoise color. Yeah, so this is, I'm just going to jump ahead to 6. This is the phenolphthalein. Again, difficult to say, impossible to spell. You don't want to drink this. It's gives very bad gastrointestinal disorders. I'll just leave it at that. So yeah, so you don't want to spill it on yourself. And of course, you don't want to, since it's dissolved in ethanol, you don't want to have this near your fire either. This is extremely flammable stuff. And you've got a ton of it. I mean, I don't know why we get so much, but there's enough here for probably like 10,000 reactions, because you only need a drop of it at a time. Okay. All right, so here's my approximately 2 mils of sodium hydroxide, and this is my phenolphthalein pH indicator. So that's 2 drops. So you can see that's so phenolphthalein in the presence of high pH or basic solution turns this really nice sort of, I don't know, what'd you call that? It's not, it's lighter than purple. It's darker than pink. No, I guess pink is fine. Sort of like a reddish pink color. So we'll take the temperature of that. Ooh, and unfortunately, I had my thermometer next to my computer fan, so now it's much warmer than it was before. So I'll just leave it in there and let it equilibrate. So now it's saying 10 degrees. Man, I don't feel that cold. I don't know. I don't know why all these liquids are so cold. Yeah, about 10.5 degrees. So now I have my 2 mils of 1 molar HCl, and carefully now pour them together. Start mixing. So as I mix, you can see what happens to the color. So it was bright pink and now it's clear again. And the temperature is going up. It was 10 degrees, it's now 16 degrees. So basically I'll keep my eye on this. And when it starts to go down again, I'll stop measuring the temperature. 17 degrees. And if the temperature doesn't change, if you have a little more sodium hydroxide than acetic acid, I mean hydrochloric acid, just add a couple more drops of the HCl to see what happens. Because as we'll learn about pH, it's based on a logarithmic scale. It's not linear. So just a tiny bit of base or acid can change the pH drastically. Let me double check the temperature again. Yeah, now it's starting to come down. Now it's only 16. So it went from 10 to 17 degrees. So is that an exothermic? Is that endothermic?
Exothermic?
It is. It's exothermic. And what we'll learn about that reaction we have HCl dissolved in water. HCl is an ionic liquid, which is unique. Most ionic compositions are solids, but this is unique. It is a liquid. And when it's dissolved in water, we get H plus and we get Cl minus. So we get hydrogen ions and we get chloride ions. So then when I add sodium hydroxide in water, I get sodium ions and I get hydroxide ions. Now we know that when we have sodium ions and chloride ions in water, they're just happy hanging out. We can dissolve a ton of salt in water and it doesn't precipitate. So sodium ions and chloride ions in solution are very, very happy and they don't react with each other. So the only other reaction that could actually be taking place is between hydrogen ions and hydroxide ions. So if I have sodium or hydrogen ions and I mix those with hydroxide ions, what do you think my product is? I have H plus aqueous plus OH minus aqueous. What do you think they make when they come together? Well, what would their product be? H plus plus OH minus. Anyone want to take a guess what that would make? Everyone's too busy doing their experiments. Right, last chance. H plus plus OH minus. What do you think I'm going to make with that?
Isn't that just water?
That's right. That's just going to make water liquid. And that's what we call a neutralization reaction. So we'll learn more about these reactions a little bit later. This is a neutralization reaction because it takes an acid and it takes a base and it neutralizes them into water. And the other product is a salt. And our salt in this case is NaCl. So that's what happens when you take a strong acid like HCl and a strong base like NaOH, you mix them together. They neutralize each other to form water and a salt in that water. The salt in the water, depending on what other ions are with the H plus and the OH minus. So yeah, good job. And that's our chemical reaction, is H plus plus OH minus makes water. And it's also an exothermic reaction. Because water is so stable. Water is very, very stable. It's very low energy. So you take two high energy things, you mix them together to make a low energy thing. That energy's got to be released somehow. And in this form, it's released as heat. All right, good job.
Sorry, I know you did this already, but for the copper sulfate and the sodium carbonate, would
Mhm.
that be a physical change because it changed into kind of like a solidified substance? But it's not completely solidified, but it didn't change like the color or anything.
That's a good point. Yeah, because when we added the water to the sodium polyacrylate stuff, that made a big swelled up, and you could say, it made something. But in that instance, we took a solid, something that was already solid, and we just turned it into a fat solid. So we didn't really change its state. It was a solid before, and it's a solid after. It's just bigger. So we changed its size, but we didn't really change its state. With the copper plus the carbonate, we took a liquid and another liquid, and we mixed them together and we formed a solid.
Mhm.
So that is a chemical reaction.
Okay.
Yeah, that's the difference. That's a really good question, because we took something, it looked the same as before, but it was in a different form. Yes, but it was soluble before. It was a soluble ion, and then we turned it into an insoluble ion. That's a chemical reaction. See if there's one more I can do here. Oh yeah, should do the copper sulfate with the aluminum. That's a good one. It's real messy. Let me clean out some test tubes. I'm gonna get some salt for this one. Yeah, make sure when you put these back, make sure you have the tops really tight on them. Because we don't want these leaking. Right, so we just get some table salt. You don't have to be super precise with the table salt for that last one. But I may need more than that. All right, so I've got my 5 mils of copper sulfate. And I'm adding it to my table salt. So notice what I get here. So there's my table salt at the bottom. And it really hasn't started going into solution yet. But note the color change. It's gone from green, or gone from blue to green. And then remember what I told you about the Lady Liberty out in New York Harbor. So what do you think our product is down there? And you mix and mix and mix. It doesn't really seem to want to go into solution, which is odd. Because sodium chloride should be fairly soluble. You mix and you mix and you mix. And you come to the realization that they may not be sodium chloride anymore. Oh, now more of it's going into solution. Now you can see almost all of it now is green, whereas before it was blue. Now it's pretty much all green. And those crystals that were at the bottom are now white. Whereas they were green before, they're now white. So what do you think those white crystals are at the bottom of our solution here? Yeah, now there's only a very few of them left. Few. And so this is the original color of my copper sulfate, and then this is the color of it now. Then, so there's a second. Oh, what you got there, Emily?
This is the copper 2 sulfate and the sodium bicarbonate.
Oh,
or, sorry,
right.
Sodium
Mhm.
carbonate.
Yeah, that happened fast, didn't it? That was almost instantaneous when you mix them together.
Yeah.
Yeah, that happened super, super quick. This one takes a little bit longer because you got to get all that sodium chloride into solution. There may be a little bit left over in the bottom, but basically we have changed copper 2 into copper 1. So that's why it's gone from blue to green. So now I'm going to do the second part. So we need to get some tin foil, or actually not tin foil, aluminum foil, and cut it into some small pieces. First, I'm going to get the temperature of the solution. Leave that in there. I think you're going to be fairly surprised by what happens with this one. All right, let me go get some aluminum foil. We just got some here. You can see it's your regular sort of shiny. You can just tear it into some small pieces. Make sure you can get them into a shape that can go into the test tube. Okay. So my new copper 1 solution is, like always, 11 degrees. So I'm going to throw my aluminum in. So now I put some aluminum in there. And you should be able to see some things happening. What's the first thing you notice?
Bubbling.
It's, yeah, oh yeah. There's a lot of gas being produced. Also, what's happening to the aluminum?
Is it oxidizing?
It's turning color. We don't know actually what it's doing yet, but it's definitely changing color. It's turning brown, actually. And if we measure the temperature, the temperature is basically doubled, more than doubled. It's gone from 10 to 25 degrees. And if you actually feel the sides of it, it's warm. So it's a very, very vigorous reaction. Still see plenty of bubbles forming. And whatever aluminum is left, it's being basically coated by this brown, sort of nasty brown coating on the outside. So what's actually happening here is we're basically plating the aluminum with copper. The aluminum and copper are changing places. The aluminum is becoming a +3 ion, and the copper is going from being +1 to 0, just being metallic copper. So we're forming metallic copper. You see this sort of copper color, regular copper color. It's not blue or green anymore. It's now sort of like a brownish color, which is the regular color of copper. So we'll learn a little bit later that what we call this reaction is actually called a redox reaction or an oxidation reduction reaction. And what that means get my, oh, here we go. So what that means is that initially we had, oh, make that a little bigger. Initially we had copper 1 and we had solid aluminum. When we mixed them together, this was copper ion, aqueous, and this was solid aluminum. Then this became copper solid, and this became aluminum +3 aqueous. So which one of these gained electrons and which one of them lost electrons? Did the copper gain or lose electrons in this reaction? This is what we started with, and this is what we ended with. Did it gain electrons or did it lose electrons?
It gained an electron.
It did, that's right, it gained an electron. 1 electron went from copper plus to copper. So we call this a reduction, because its charge was reduced. It went from being +1 to being 0. And what about the aluminum? Did it gain electrons or did it lose electrons?
It lost 3 electrons.
It did. It lost 3. That's right. Excellent. It lost 3 electrons. So it went from having a charge of 0 to having a charge of +3. We call this oxidation. And the usual, why we call it that is that usually it's done a lot of the time by oxygen. Because oxygen likes nothing better than taking electrons from other atoms. So the copper was reduced from +1 to 0, and the aluminum was oxidized from 0 to +3. So what happens if we were to balance this reaction? We would have to balance the number of electrons. And so in fact, 3 ions of copper were reduced with 3 electrons to 3 neutral copper atoms, while 1 aluminum was turned into aluminum +3. So that gives us 3 electrons on one side of the reaction and 3 electrons on the other side of the reaction. So that's an oxidation and reduction reaction, which is super, super common. Most chemical reactions are oxidation reduction reactions because electrons go from one place to another place, from one atom to another atom. Yeah, this just makes an ungodly mess though. That aluminum just looks so, it was so nice and shiny, and now it's just so nasty looking. And what's our final temperature? It's still super warm. It's still producing gas. Oh my gosh, yeah, now it's like 37 degrees. So that one is a dramatic. I said, yeah, they're not always going to be super dramatic changes in temperature. This one is. So this one went from 10 to 37 degrees. That's fairly impressive. 38 now. So still not done. Still got some bubbles going. Hardly any aluminum left though. You see there's hardly any shiny pieces of aluminum. They've all been turned into ions. And we get copper. So if we were to spin this, basically we get a big puddle of copper metal on the bottom. So anybody have any questions about what they've been doing so far? Which reaction are you guys up to?
I'm doing the water and sugar one.
I can't remember if I don't know if you see a change in temperature with that one or not. I don't think so. Yeah, that's just sugar going into solution. Don't think it changes the temperature. But there are things going on in the water. You've got basically water molecules interacting with each other. And then when you dump the sugar in there, then they start interacting with the sugar. So there is some change of who water is interacting with, but no chemical bonds are broken.
Beaker stuff from like down
Yeah.
the
Yeah, if there's no solids in there, you can just go ahead and just dump it down the sink, because yeah, there's nothing dangerous, there's nothing toxic in there. The only things that were a worry are the strong acid and the strong base, but you mix those things together to neutralize. So now it's just
Okay.
water and salt. You can
So
dump it.
I can just, okay,
Yeah, I mean, that's basically how we dispose of strong acids and strong bases anyway. We just mix them with each other and then toss them. For the food coloring one, yeah, we just make a dilute solution of the yellow and the blue and then mix them together. If you have your own yellow and blue food coloring, you feel free to use those.
okay.
For the sodium polyacrylate copolymer, do we need to save that bag and put it back in the kit? Or should we just toss it?
We're not going to be using it again. I mean, if you want to,
Okay.
do a party trick with the Super Bowl for your friends or something, you can, you can toss it in someone's beer and turn it into a beer sickle. That might be amusing, but no, I don't think we're going to be using that one again.
And so for like when we return the lab kit, I think like for renting it, we have to return like basically the whole thing, like.
I think all they're gonna want is, at least last term, all they wanted was, I think, the copper sulfate, the phenolphthalein, and I think that was it. I think those were the only two things they were looking for. Because
Okay,
because those things are kind of, yeah, you don't want to pour like copper sulfate down the sink, like a really lot of it concentrated at once. Little bits of it is fine, but I think that was all they wanted.
okay,
They didn't even want like the supplies back. So you now have a balance you can use in your kitchen for baking. It only goes up to 100 grams, but
okay, sounds good. I think I'll just put the kit together, just in case.
yeah, I'm just going to give it to my son. He can play with it. It's fun to throw it in a glass and like make it expand. But that's basically the only thing it does. Phenolphthalein is how we pronounce it. Phenolphthalein. What about
Would
it?
that be a chemical change because it changed the color and appearance of it, and it changed into it's a different chemical composition.
What's your evidence that it's a chemical reaction?
The change of appearance and the I'm not.
Yeah, so there's two things happening in that particular reaction. One, with the sodium hydroxide, that is just a color change, right? When you added your 1 or 2 drops of phenolphthalein. The
And
phenolphthalein is clear, right? It doesn't have any color.
Yeah.
The sodium hydroxide doesn't have any color, but when you mix them together, get this bright pink color.
Mhm.
So that's evidence of something.
And
Then what
heat
happened?
exchanger?
What happened when you added the HCl to it? Have you done that part yet?
No.
Something magical will happen. Because the phenolphthalein undergoes what we call a reversible reaction. I'll share the screen for a minute. So usually when we look at chemical reactions, we think of them going in like one direction, right? Like if we burn hydrogen gas in the presence of oxygen, we make water. And that reaction doesn't go backwards. It's not like we can just take water and it spontaneously goes back into being oxygen gas and hydrogen gas. That doesn't happen. So basically this reaction just goes in one direction. But that's not true for a lot of other reactions. And actually one of them is the reaction you're about to do. This reaction, for instance, H plus OH minus makes water. Actually goes the other way too. A little bit of water is constantly making H plus and OH minus. Not very much of it. In fact, the reaction goes to the right much more than it goes to the left, but it does go to the left a little bit. And with your phenolphthalein reaction, this being clear, and then this being pink, that readily goes back and forth, depending on the pH. If the pH is above 8, it's pink. But then anytime the pH drops below 8, it's clear again. And it can go back and forth and back and forth and back and forth, like however many times you want. Because that reaction is readily reversible. So not all reactions are, but the reaction of phenolphthalein changing color definitely is. So you can add acid and it goes clear, you can add more base, it turns pink, add more acid, it goes clear, add more base, it turns pink, and on and on and on. Isn't that right, Jerome?